Hello everyone, welcome to Module 2, which is going to be on fractions, and we'll look at all sorts of things about fractions. We'll look at operations on fractions, multiplication, division, addition, subtraction, etc. But I want to start by talking about the first section, 2.1, which is simply on factors and prime numbers. Okay, this will be very important later when we talk about the operations that we want to do with fractions. So looking at factors, if I have some multiplication problem, say like, 2 times 4 is equal to 8. In this case, the 2 and the 4 are called factors of 8. So 2 and 4 are factors of 8 because they multiply to give me 8. Okay, or another way of saying it is they divide 8 evenly, right? Each factor divides 8 evenly. So what you're going to be asked to do is find factors of particular numbers. So to do that, let's say, for example, we want to find all factors of 10. What I would do is start with the obvious one. We know that 1 times the number gives us a number, right? So certainly if I do 1 times, sometimes I write times like that. Sometimes I just use a dot here. They both mean multiplication. So 1 times 10, that will give me 10. Then I work my way up. Does 2 go into 10 evenly? Yeah, so 2 times 5, right, will also give me 10. And then try 3. No, 3 doesn't go into 10 evenly. 4 doesn't go into 10 evenly. And then if I get to 5, I've already dealt with 5, so I can stop. Okay? So what this tells us is that basically 1, now I'll just list them in order. 1, 2, 5, and 10 are factors of 10. Okay, here's another one. Find all factors of 48. Okay, so I start with the obvious, right? 1 times 48. That will certainly give me 48. Then I work my way up. 2. Does 2? Yeah, 2 definitely goes into 48, right? So 2 times 24. Does 3 go into 48? So you might have to go on the side over here and do divide by 3. I'll give you guys some quick divisibility rules in a second, but let's just do this out. So yeah, it looks like 3 goes in, right? Because 3 goes into 4 once. And then I subtract, bring down the 8. 3 goes into 18 6 times. So 3 times 16. Does 4 go into 48? Yeah, 4 times 12, right? Does 5 go into 48? No, 5 doesn't go into 48. Does 6? Yeah, we know 6 times 8 gives us 48. And then does 7? No, 7 doesn't go in evenly. And if I get to 8, I've already dealt with 8, so I can stop, right? So the factors that go into 48 are going to be, I'll list them in order again. 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48 are factors of 48. And again, you can think of them as ultimately they divide, all those factors, all those numbers divide 48 evenly, right? That's the best way to think of it. Okay, so a quick way to find factors is to use divisibility rules. So let me just remind you of the divisibility rules. Okay, so here are the divisibility rules. So how do we know if a number is divisible by 2? Well, a number is divisible by 2 if the last digit is an even number, right? So if the last digit is either a 0, a 2, a 4, or 6, or 8, then we know it's divisible by 2. So for instance, if I have some number, it could be a very large number. I'll say, is this number divisible by 2? And then you would look at the last digit. Oh yeah, that's an even number, right? So therefore, it is divisible by 2. Yes. Now, it doesn't tell us what the value is. We'd have to actually do the division out, but it tells us that it's divisible by 2. Okay, how about 3? How do we know? What's a quick way of determining whether a number is divisible by 3? Well, what you do is you sum the individual digits, and if that is divisible by 3, then the original number is also divisible by 3. Okay, so for instance, if we use the same number that I just checked up here, if I add these together, let's see if this one's divisible by 3 or not. I'm going to add all these digits together. 7 plus 3 plus 2 plus 5 plus 0 plus 4. So what is this? 10, right? Plus 2 is 12, plus 5 is 17, plus 4 is 21. And since 21 is divisible by 3, right? 3 goes into 21 evenly 7 times, then this number is divisible by 3. The original number is also divisible by 3. So that's yes again. Okay, how do I know if a number is divisible by 4? Well, if the last 2 digits, right, taken as a number, or named, or the number named by the last 2 digits, another way of saying this, if those are divisible by 4, then the number is divisible by 4. So actually in this case, again, the last 2 digits, right, are 0 and 4. So that's just 4. And is 4 divisible by 4? Yes. So this number is divisible by 4. Yes. If you had something else, right? Let's say you had, 2, 3, 1, 5, 2. Is this number divisible by 4? Well, you have to look at the last 2 digits. 52. Divide 52 by 4. Does it go in evenly? Actually, yeah, it looks like it does, right? So 4 goes into 12 3 times, so it goes in 13 times. So yes, this number is also divisible by 4. Okay, so you just have to check the last 2 digits, which makes it a lot quicker, right? Especially if you have a very large number. Okay, how do we know if a number is divisible by 5? Well, this one you guys definitely know, right? If the last digit ends in either a 0 or a 5. So was our original number divisible by 5? No, definitely not, right? Because my last digit is a 4. It's not a 0. It's not a 5. So this is not divisible by 5. So this would be, no. Let me write it here. So this is yes. This is yes. This is yes. In this case, this is no. Okay, 6. What's the rule for 6? I know a number is divisible by 6 if it's both divisible by 2 and 3. So in this case, is this large number, right, 732,504, is that divisible by 6? Well, in this case, it's divisible by 2, right, and 3, so the answer is yes. If it passes both of those, it's also automatically divisible by 6. Okay, why is 7 not here? There is a rule for 7, but it's more complicated than it's worth. So it's often easier just to divide it just do long division by 7 and then see if it goes in evenly or not. Okay, the rule is more complicated, so most books, some books will include it. You can look it up, but we're just going to skip that. So we'll go right to 8. The rule for 8 is if the last 3 digits taken as a number is divisible by 8, then the original number is divisible by 8. So let's check our number again. So now I have to look at 504. So is that divisible by 8? Let's do it over here. Let's see, how many times does 8 go into 50? I guess it's 6, right? So this would be 48. 50 minus 48 is 2. I bring down the 4. 8 goes into 24 3 times. Oh, my remainder is 0. So yeah, I guess it is. So since the last 3 digits is divisible by 8. The entire number, the original number, is also divisible by 8. Well, this is working for a lot of these. This is sort of luck. Okay, how do I check 9? Well, 9 is very similar to 3, right? I have to look at the sum of the digits. If the sum of the digits is divisible by 9, then the original number is also divisible by 9. Well, we already did this one, right? Remember we had, if I add these up, 7 plus 3 plus 2 plus 5 plus 0 plus 4, I got 21. 21 is not divisible by 9, right? 9 doesn't go into 21 evenly. Therefore, that original number, the large number, is not divisible by 9. So this is no. And in 10, you guys definitely know, right? Remember, how do we know if a number is divisible by 10? If the last digit is a 0. So in this case, that last digit is a 4, right? It's not a 0, so it's not divisible by 10. So this is no. Okay, so, I mean, if you forget these rules, it's okay. You can always, just do long division. If it goes in evenly, then it is divisible by that particular number. These are just a quick way of determining whether a number is divisible by 2, 3, 4, 5, 6, 8, 9, and 10. Okay, let's do another example with divisibility rules. So we want to figure out if this number, so 171,252, so 171,252, is divisible by 2, 3, 4, 5, 6, 8, 9, 10. Okay? So divisible by, and we're going to check all of our numbers, right? So 2, 3, 4, 5, 6. We'll skip 7 and 8, 9, 10. Okay, is it divisible by 2? Yes. How do we know? It ends in 2. Right? The number ends in 2. Remember, if the ones digit is even or 0, then it's definitely divisible by 2. Is it divisible by 3? Well, we need to check. We need to add the digits, right? We have to find the sum of the digits. So if I add 1 plus 7 plus 1, that's 9, plus 2 is 11, plus 5 is 16, plus 2 is 18. And since 18 is divisible by 3, right? 3 goes in 18 evenly, then 3 also goes into that whole number, the 171,252, evenly. Right? We just have to check whether it goes into the sum of the digits evenly. And it does, so it definitely is also divisible by 3. Okay, to check 4, remember we have to check just the last 2 digits. So I have to see whether 52 is divisible by 4. And yeah, it is, right? It goes in 13 times. So this number, right, the original number, is also divisible by 4. So that's yes. Is it divisible by 5? Well, remember, the last digit has to be either 0 or a 5, right, for it to be divisible by 5, the ones digit. And it's not, so this is no. Is it divisible by 6? Well, the rule for 6 is it has to be both divisible by 2 and 3. And since we have yeses on both of those, right, it's divisible by 2 and 3, it automatically is divisible by 6. So that's yes. Is it divisible by 8? Well, to check 8, I have to look at the last 3 digits, 252, and see if that is divisible by 8. Right? Does 8 go into that evenly? So let's see, 8 goes into 25 3 times, right? So this is 24, subtract, bring down to 2. 8 goes into 12 once, multiply 8, and then I subtract, I have 4. So it looks like no, because I have a remainder, right? 31, remainder of 4. It doesn't go in evenly. So since it doesn't go into the last 3 digits evenly, then the original number is not divisible by 8. So this is no. Is it divisible by 9? Well, remember, 9 deals with the sum of the digits again, right? And we already found that earlier. If I add up all these digits, I got 18. And 18 actually is divisible by 9, right? 9 goes in 18 exactly 2 times. So that original number, right? The whole number is divisible by 18. That's yes. And then is it divisible by 10? Well, we only have to check the last digit, right? It has to be a 0. It's not, it's a 2. So this is going to be no. Okay. Again, if you forget these rules, that's okay. But they are kind of nice because they give you a quick way of determining whether a number is divisible by a particular number. So basically, it's a quick way to find factors, right? If you want to find factors of numbers. Okay, next I want to talk about prime and composite numbers. So prime, let me do this and composite. Okay, so what is a prime number? A prime number is a whole number that has itself and 1 as factors. So it's a whole number that I'll say only has itself and 1 as factors. Or another way of saying that is it's only divisible by itself and 1 evenly. So it is only divisible by itself and 1. And when I say divisible, I mean divisible evenly, right? A composite number has more than 2 factors. So say has more than 2 factors. Now, by definition, right, 0 and 1 are kind of special numbers. They're neither prime nor composite. So I'll just write they are neither prime nor composite. They're like special cases. So we kind of ignore, when we talk about prime and composite numbers, we ignore 0 and 1. We start with 2. Okay, and in any other whole number, so from 2 on to infinity, any number in there is going to be either prime or it'll be a composite number. Okay, one or the other. All right, so let's start by naming like the first 10 prime numbers, okay? So I'll do here an example. Say you want to name the first 10 prime numbers. Okay, so the first prime number is actually 2. In fact, it's the only even prime number because any other even number would be divisible by 2, right? And then it couldn't be prime. Like 4 is divisible by, it has factors of 1, 4, and 2. So it has more than 2 factors, right? Not just 1 and 4. So any other even number would be divisible by 2, so it cannot be prime. It has to be composite. 2 is the only even prime number. Then I work up my way up. 3. Yeah, 1 times 3 is the only way I can get 3, right? So 3. 4 is definitely not prime, so I go further. 5, yeah, 1 times 5 is the only way I can get 5. So 5 is prime. 6, nope, 2 times 3 will give me 6, right? So 6 is not prime. 7 is definitely prime. 1 times 7 is the only way I can get 7. 8, that's not prime, right? Because 2 times 4 will give me 8. 9, 3 times 3. 10, 2 times 5. So none of those are prime. Let's see. Next one is 11. Yeah, 11 is prime because 1 times 11 is the only way I can get 11. 12 is not 4 times 3 and 2 times 6, right? There's many factors of 12. 13 is prime. only 1 and 13 are factors of 13. 14 is not, because it's even. 15 is not, 3 times 5. 16 is not. 17 is. 18, no, it's even. 19, yes, 19 is. How many do we have so far? 1, 2, 3, 4, 5, 6, 7, 8. So 2 more. Let's see. 20, no, right? Because it's even. 21, 3 goes into it. 7 goes into it. 3 times 7, so that's not. 22 is even. No. 23, yes, 23 is prime. Then 24, no. 25, 5 times 5, no. 26 is even, no. 27, no. 3 times 9, right? 28 is even, no. 29 looks like the next one. And so on, right? So these numbers are only divisible by themselves and 1. That's it. Or they only have themselves and 1 as factors. So those are the prime numbers. Now, what about let's see if we can name the first 10 composite numbers. Well, this is basically filling in the gaps here, right? So because we skipped the ones that weren't prime, right? So they have to be composite. So name the first 10 composite numbers. So start with, let's see, I guess it'll be 4, right? 4. Then 5 was prime. 6 is composite. 7 is prime. 8, 9, 10. Right, those are all composite. 11 is prime. 12 is composite. 13 is prime. 14, 15, 16. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I just need one more. And then I guess, 17 is prime. 18, right, is composite. And so on. Right, and then 20, 21, 22, 24, 25, 26, 27, 28. Those are all composite as well. Okay, so why are we learning this? Because there's a very special way of factoring numbers. It's called the prime factorization, and we use it all the time. We're going to use it to find what's called the lowest common multiple. When we want to add fractions, we're going to need to know the lowest common multiple. So this is a very important factorization. It's called the prime factorization. So basically, what this is I can take any whole number, right, that's not 0 and 1, and either it's already prime, or it can be written, if it's composite, it can be written as a product of prime numbers. So really what we're saying is any I'll write whole number greater than 1, right? Because remember, 0 and 1 are special cases. They're neither prime nor composite. So greater than 1 is either prime itself, or if it's composite, it can be written as a product of prime numbers. Okay, so again, the way to think about this is any composite number can be written as a product of prime numbers. Okay, and actually, this has a name. It's called the fundamental theorem of arithmetic. So fundamental theorem of arithmetic. Okay, so again, it says that any whole number greater than 1 is either prime itself or it's a composite number, and if it's composite, it can be written as a product of prime numbers. And there's actually only one unique way of writing that product of prime numbers. So it can be written as a product of primes, and there's only one way of doing it. Okay, so let's review how to find the prime factorization. And we're going to use this technique where we use a tree, okay? Okay, so how do we do this? Let's do an example. Let's say we want to find the prime factorization of 40, right, of the number 40. So 40 is a composite number, right? It's not already prime, but we just learned that it can be written as a product of prime numbers, okay? So the way I do this, again, is like with a tree. I branch off of 40, and there's two possibilities, right? Branching. Now remember, the prime numbers are 2, 3, 5, 7, and so on. There's several ways you can do this factorization. The way I like to do it is I always start with the lowest prime number, 2. Does 2 go into 40 evenly? Yes, 2 goes into 40 20 times, right? Now I leave the 2 alone because that's prime. I branch off to 20. It's still composite. I start with 2 again. Does 2 go into 20 evenly? Yes, it goes in 10 times. So 2 times 10. Then I leave the 2 alone again. I branch off to 10. I can still stay at 2. Does 2 go into 10 evenly? Yes, it goes in 5 times, right? 2 times 5 gives me 10. And now I stop. Why? Because all of these numbers are prime now. 2, 2, 2, and 5. So this tells me that 40 is the same as 2 times 2 times 2 times 5. That's the prime factorization. Now, often people will write it like this. They'll use exponents, right? And write it in terms of powers. So remember, 2 times 2 times 2, we could write as 2 to the 3rd power times 5 to the 1 power, but we don't write the 1 there. Okay, so 40 is 2 times 2 times 2 times 5, or 2 to the 3rd times 5. That's the prime factorization. I wrote this number 40 as a product of prime numbers. Okay, here's another example. So find the prime factorization of, let's say, 90. Okay, so I start with 90. I draw 2 branches. Let's see, does 2 go into 90? Yes, we know from our rules, right? It's even, right? Ends in a 0. So 2 goes in 90. If you work this out, it's 45 times. Does 2 go into 45? No, right? Doesn't go in evenly. So I work my way up. Remember, the next prime number is 3. Does 3 go into 45? Well, the quick way of telling, remember, if you add the digits, 4 plus 5 is 9, and 3 goes into 9, so 3 must go into 45. And if you work it out, if you divide it out, it's going to be 15 times. I'm still at 3. Does 3 go into 15? Yeah, 3 goes into 15 5 times. And then I stop because now all these numbers are prime. Right? So 90, if I want to know its prime factorization, it's got to be 2 times 3 times 3 times 5. Or I could write it as 2 times 3 squared times 5. Okay. What about the prime factorization of 63? So I start with 63, branch off. Does 2 go into 63? No, right? It's not even. Does 3 go in? Yeah, it has to, right? Because the sum of the digits, 6 plus 3 is 9, and 3 goes into 9. So it must go in, and if you work this out, it goes in 21 times. So then I branch off to 21. Does 3 go into 21? Yeah, 3 goes into 21 7 times, right? And 7 is also prime, so now I can stop And we know that 63 is the same as 3 times 3 times 7, right? That's the prime factorization. Or I could write it as 3 squared times 7. Okay, so very important concept. In fact, it's going to be used in the next concept that we look at, which is called least common multiple. So let's talk about that next. So least common multiple. Some people will also say lowest common multiple, but usually it's the least common multiple. So first of all, what is a multiple of a number? A multiple of a number is the product of that number and a natural number. So, for example, let's say I want to find some multiples of 8. Okay, so remember the natural numbers right over here are the counting numbers, right? 1, 2, 3, 4, and so on. So basically, one multiple of 8 would be 8 times 1. So 8, right? 8 is also a multiple of 8. Then 8 times 2, which is 16. That would be a multiple of 8. 8 times 3, which is 24. That would be a multiple of 8. 8 times 4, which is 32. That would be a multiple of 8, and so on. Okay? So that's all I mean by multiples. They're just a product of the number and some natural number. Okay, so what about this whole idea of least common multiple? So the least common multiple which is often abbreviated LCM. So when you hear LCM, we mean least common multiple of 2 or more whole numbers. I'll just start with 2 right now. So of 2, but this also applies if you have more than 2 numbers. So of 2 whole numbers is the smallest number that is a multiple of both. So is the smallest number that is a multiple of both. Okay, so for example, let's say I want to find the least common multiple, I'll just abbreviate LCM, of 10 and 15. Okay, so I want to find the smallest number that is a multiple of both. And you might be able to do this in your head, but let's actually find the multiples first. So what are all the multiples of 10? Well, 10 times 1, right, which is 10. 10 times 2, which is 20. 10 times 3, which is 30. 10 times 4, which is 40. 10 times 5, 50. 10 times 6, 60. 10 times 7, 70, and so on, right? Those are all the multiples of 10. What are the multiples of 15? Well, 15 times 1 is 15. 15 times 2 is 30. 15 times 3 is 45. 15 times 4 is 60. 15 times 5 is 75, and so on, right? Those are all the multiples of 15. So the least common multiple is going to be the smallest number that is a multiple of both. So if you look at these lists, right, what's the smallest number that's a multiple of both 10 and 15? it's the 30. Right? So see how 60, right, is a multiple of both, but it's not the least common multiple. So the least common multiple is the smallest number that's a multiple of both. So in this case, we would say 30 is the least common multiple. So 30, right, is the least common multiple. Again, 60 and others, right, are multiples, but they're not the least common multiple. And we always want to find the least common multiple. Okay, so that's what it means, right, to be a least common multiple. But you don't want to actually solve the problem this way because the numbers could be very complicated and you don't want to write out all the multiples and then search for the lowest one. You could do it that way, but it would take a lot of time. There's a much better way of doing this, and it involves prime factorization. So that's why we spent so much time talking about prime factorization. So let me give you the rules for how to do this using prime factorization. So finding least common multiples by prime factorization. Okay, so first step, find the prime factorization of each number. So that you need to do that first. So find the prime factorization of each number. So remember, we do the tree, right, for each number. Okay, then second step, you want to identify the prime factors that appear in each factorization. So identify the prime factors that appear in each factorization. Okay, and then third step is multiply these prime factors. So multiply these prime factors using each factor the greatest number of times that it occurs in any of the factorizations. Right? This will make more sense when we start looking at some examples. So using each factor, but let me write down the rules first. Each factor, the greatest number of times that it occurs in any of the factorizations. In any of the factorizations. Okay, so again, the rules are find the prime factorization of each number. You need to do that first. Identify the prime factors that appear in each of the factorizations. And then multiply these prime factors using each factor the greatest number of times that it occurs in any of the factorizations. Okay, so let's do some examples to figure out how this works. Actually, let me start off with the one that we did, right, with the 10 and 5. So let's find I'll write it this way. Lowest common multiple of 10 and 15. Sorry, it was 10 and 15. Okay, so But I don't want to write out all the multiples of each of those numbers, right? And then pick the lowest one like I just did. I want to do it using prime factorization. So I need to find the prime factorization of each number. So I do my tree, right? Branch off to 10. Start with the lowest prime number, 2. Does 2 go into 10? Yeah, it goes in 5 times, right? And I stop because they're both prime now. And in 15, I ask myself, does 2 go into 15? No. So I work my way up. Does the next prime number 3 go in evenly? Yeah, 3 goes in 5 times. And then I can stop. So really 10 is the same as 2 times 5. And 15 is the same as 3 times 5. Okay? So now look at all of your prime factors. You have 2s, 3s, and 5s. Okay? So ask yourself, let's start with the 2. How many times does a 2 occur in this factorization, right, with the 10 here? Well, it occurs once, right? I have 1, 2 here. So it occurs once. So I need to take the 2, so once, and then I go over to the 15. How many times does the 2 occur in this factorization? It occurs 0 times, right? There's no 2 there. So what's the greatest number of times that the 2 occurs in either of these factorizations? It occurs once here, 0 times here. So I need to take it the greatest number of times, which is once. So I just take the 2 once. And I'm forming a product, so I'm going to multiply all these. Now let's look at our next number. Let's say 3. We'll do it in numerical order. So look at the 3. How many times does the 3 occur in this factorization? 0 times, right? How many times does the 3 occur in this factorization? Once. So the rule is I need to take it the greatest number of times it occurs in either of the factorizations. So I need to take the 3 once. Then I look at the 5. How many times does the 5 occur in this factorization? It occurs once. And over here with the 15, it also occurs once, right? So it's a tie. So the greatest number of times that 5 occurs in either of the factorizations is still going to be once, right? It's a tie. We just want the greatest number of times. So that's just going to be once. I'll take it 5. Write down a 5 there. So now if I multiply these out, right, I find the product. 2 times 3 is 6, times 5 is 30. Remember, that's exactly what we got when we listed out all the multiples. Right, so we're just going to be 30 in this case. Okay, here's another example. I'll do a few of these. Say we want to find the LCM of 20 and 21. So let me factor these, right? 20 and 21. So this is 2 times 10, 2 times 5. So really this is 2 times 2 times 5. 21, well, 2 doesn't go in, but 3 goes in 7 times. And actually, I can stop, right? They're both prime. So this is just 3 times 7. So now I look at each of my factors. I have 2s, 3s, 5s, and 7s. And I want to take each factor the greatest number of times it occurs in either of the factorizations. So I start with the 2. It occurs twice here, 0 times here. So I have to take it the greatest number of times, which is twice, right? So let me do the work over here. So I have 2 times 2. I take it twice. Now I go to the 3. 3 occurs 0 times in this factorization. It occurs once here. So what's the greatest number of times? Once, right? So I need to take the 3 once. Now I go to the 5. It occurs once here, 0 times here. So the greatest number of times I need to take it, or that it occurs in either of the factorizations is once. So I need to take it once. And then the 7, 0 times here, once here. So I need to take the 7 once. And if you multiply all these out, you're going to find that this is equal to 420. Okay, which actually is 20 times 21. And the reason why just the product of the two original numbers is the lowest common multiple is that there were no common factors, right? There were no common factors between each of these. So I couldn't simplify that any further. So 20 times 21 is going to be our lowest common multiple. But we find that by using the same rules that we do as usual, okay? So this is going to be our lowest common multiple, 420. Okay, here's another example. Let's say I'm going to find the LCM of 15 and 60. Okay, so let me find the prime factorization of each number. So 15. Does 2 go in? No. Does 3 go in? Yeah, 3 goes in 5 times. And I can stop, right? Because they're both prime. So 3 times 15. 60. Does 2 go in? Yep. It goes in, I guess, 30 times, right? Branch off to 30. Does 2 go in? Yep, it goes in 15 times. And then 15 is 3 times 5. So this is going to be 2 times 2 times 3 times 5. So my factors are 2, 3, and 5. So let's start with the 2. In the left factorization, right, with the 15 here, how many times does 2 occur? 0, right? 0 times. How many times does it occur in the right factorization? Twice. So I need to take the 2 twice. So it's 2 times 2. I go to the 3. How many times does the 3 occur in this factorization? Once. In this factorization, also once. It's a tie. So the greatest number of times is still just 1. And then I go to the 5. How many times does the 5 occur? Once. Here is also once. So I need to take the 5, the greatest number of times, which is once. And if you multiply that out, notice you're going to get 60, right? So it turns out that one of these numbers, the larger number, could potentially be the lowest common multiple. So what we're saying is 60 is the smallest number that 15 and 60 will go into evenly, right? 15 goes into 60 4 times, 60 goes into 60 once. So 60 is the lowest common multiple in this case. By the way, another way that you can do this is you could write these with their exponents. So I could write this as 3 to the 1 times 5 to the 1. We normally don't write the 1, but just to remind you that the exponent is really a 1 there. And this one would be 2 squared times 3 to the 1 times 5 to the 1. And then when you're trying to find the lowest common multiple, you just take the factor with the largest exponent. So in this case, 2 doesn't even occur on the left-hand side. If you want, you could put it here if you write 2 to the 0, because by definition, anything to the 0 power is equal to 1. If I multiply by 1, I'm not changing anything. So really now, if we compare these, right, I have 0 and 2, if I just look at the exponents. So I'm going to take it twice, right, because 2 is the wins out. Here, with the 3, I have 3 to the 1, 3 to the 1. It's a tie, so I just take it once, 3 to the 1. And then 5 to the 1, 5 to the 1, it's a tie, so I just take it once. So some people will write out the factorizations with the exponents, and then they just take each factor with the largest exponent. And that is exactly the same thing, right? When we say take it the greatest number of times that occurs in either of the factorizations, we really mean with the largest exponent. What if you have more than 2 numbers? Here, I'll just do a small one, so it's not too crazy. Find the lowest common multiple of, let's say, 6, 8, and 12. Actually, can you, if you think about this, right, just pause this for a second. Can you think of the lowest common multiple of 6, 8, and 12? Like, what's the smallest number that 6, 8, and 12 will go into evenly? So typically it's larger than any of them, right? It could be it could be the largest one, but typically it's larger than any of them. So what number do 6, 8, and 12 go into evenly? What number do they divide evenly? And you might come up with, 24, right? It looks like they all divide 24 evenly. So it looks like 24 is our lowest common multiple. Well, let's check it. I'll factor the 6. So prime factorization, I'll do the tree. This is going to be 2 times 3, right? I'll factor the 8, so that'll be 2 times 4, but then I can branch off to 4, and this is 2 times 2, and then I'll factor the 12. So this is 2 times 6, and then 2 times 3. Okay, so 6, again, is 2 times 3. 8 is 2 times 2 times 2. If you want, you could write this as 2 cubed, and then 12 is 2 times 2 times 3. I could write it as 2 squared times 3. Okay, so I want to find the lowest common multiple. So, and my factors are only 2s and 3s, right? I look at the 2 in the first factorization. it occurs once, right? Or the exponent is a 1 here. I look in the second factorization, it occurs 3 times, and the third one occurs twice. Remember, I have to take it the greatest number of times that occurs in either of the factorization. So I need to take that 2 3 times. So 2 times 2 times 2. Now look at the 3. The 3 occurs once here, 0 times here, right? You could put a times 3 to the 0. We often don't write that, but you could. So once here, 0 times here, once here. So it's a tie, but the greatest number of times that 3 occurs in either of the factorizations is once, right? It's a tie, but it ends up being 1. So this is going to be just 1 3 there. Now if I multiply this together, 2 times 2 times 2 is 8, times 3 is 24. And that's what we guessed, right? Remember, we guessed that the lowest common multiple, the smallest number that 6, 8, and 12 will go into evenly, is going to be 24. Okay, so I think I'll stop there. This video is long enough. There's a lot to explain, but hopefully that made sense, and you can start looking at the problems in My Output Math. Great, thanks.